All right, so here comes the fun part. What if these cyclohexanes are di-substituted? So if there's two things, well, then it's going to depend on if it's cis or trans. It's going to depend on where these things are attached. If they're 1,2 substituted or 1,3 substituted or 1,4 substituted. So we're kind of look at each case independently to see if they're going to be, if it doesn't matter whether axial, equatorial, or axial, or if they're going to, one will always be equatorial and hardly ever flip to the axial. All right, so di-substituted cyclohexanes. Now we're going to have these steric effects for two substituents. So we're going to start by looking at 1,2-dimethylcyclohexane. So in other words, there's a methyl group on number 1 and there's a methyl group on number 2. So they're on neighboring carbons, two carbons that are right next to each other. And of course, now we know that there's two possibilities. They can either be cis, where they're on the same face, or trans, where they're on opposite faces. I think we'll see pictures in just a second, but again, remember that every carbon, every other carbon had axial going up and then equatorial and axial going down. So every other one had an axial going in a different direction. And so if you have two neighboring carbons, cis, well, let me see if I can draw this. Oops, that's got to go like that. I'm not very good at this. Let's erase that. Draw this here. All right, so if we're talking 1 and 2, so here, let's do another color. I'll go back to the blue for. So what I want you to notice here, let's get my pointer back, is that, no, maybe I better use my pen again. So let's say I've got a methyl group here. All right, up here on the top, so that would be axial. What would cis look like? Well, remember, cis means the same side. So this is the top. Maybe that's what I should write. Let's see. Let's use yellow. So this is a top and this is a bottom, right? This is a top and this is a bottom. So for it to be cis, they need to both be either top or either bottom. So if I have a methyl group here, then cis would have the X. You can see that there. Cis would have top and top. But what I also want you to notice is that, see if I could use another color, this color. What I also, so we've got, that makes it a little darker. So cis are both, but what I want you to notice that if it's cis, top and top, one is equatorial, this one's equatorial, and this one's axial. What happens if you ring flip this? If you ring flip this, this one will become equatorial and this one will become axial. So there'll still be one of each, one equatorial, one axial. So what that tells us is that in cis 1, 2, both conformations are equal energy, because you're always going to have one equatorial and one axial. Doesn't matter, as long as they're side by side, they're both tops. One's equatorial, one's axial. So they're going to be the same energy either way. So here's another picture of that. Let me get my pointer back. So again, they're both on the top. Let me draw. If I draw this axial in, they should draw the other two in. So here's the axial, here's equatorial, this is bottom, this is bottom. So both of these CH3s are top. One's equatorial and one's axial. If it does a ring flip, notice that that blue one that was on top, let me draw their axial in. Sometimes it's hard to see if you don't draw both hydrogens in. So this is equatorial, the red one's equatorial, the blue one's axial. When it does a ring flip, the blue one becomes equatorial and the red one becomes axial. There's always one axial that has the 7.6 kilojoules, and there's always one equatorial that doesn't. There's one other interaction that might be hard to see, but because these two CH3s are near each other, they actually a gauche interaction too. So both of these if you do a ring flip, they're both 11.4 kilojoules per mole, either way. So what about trans? Let me draw it here. So again, if we have trans, then that means, and it's 1,2 trans, so that means, whoops, can't see that color. Let's try this color. And they're 1,2, right? Let's do another color for the, I'll do black. So the equatorials are black. Again, if it's trans, then it means we have to have a top and a bottom. And this is a top and this is a bottom. And it looks really, this one's harder to tell. Notice that the top, one top is equatorial and one's axial. One bottom is axial and one bottom is equatorial. And so we have to have, let's try another color here. So for trans, we're going to have one on the top and one on a bottom. And so you can see in this case, they're both axial, which is very high energy because both of these will be having interactions, the 7.6, 3.8 times 2, which is 7.6, and then another 7.6 up here on top. I don't know if you can see that pointer, laser pointer. So there'll be this axial will have 7.6 kilojoules, and this axial will have 7.6 kilojoules. So it's actually very high, 15.2 kilojoules, because they're both axial. But then what happens when we get a ring flip? So here's the one that we were just looking at. They're both axial. One's on the top, and I'm going to draw in, again, I'm going to draw in, this is equatorial and this is equatorial. So these just have hydrogen on it. And we're not worried about them because they're not interacting, but I just so that you see that this is a top and this is a bottom. I can't draw very well. Even though they're both equatorial, this one's a top and this one's a bottom. Now when we do a ring flip, we end up with this one up here. And now notice, I'm going to draw these in again. This is still the top. The pink one is still a top. It's just that now it's equatorial. And this blue one, if I draw that in, is still a bottom, but it's also equatorial. So now they're both equatorial, and there are no 1,3 diaxial interactions at all. The only thing we have is one gauche interaction between these two groups because they're on carbons 1 and 2. So this is very low energy compared to both of them being axial. Laser pointer. So this one's low energy and this one's high energy. So if you've got 1,2 dimethylcyclohexane, the trans will almost always, nearly 100%, have both CH3s in the equatorial, and hardly any, it would be very low percentage, will have them both in the axial. In fact, it's almost, sometimes we call it a ring lock because it's almost always going to be found in the more stable position. Now, everything changes when we get to 1,3-dimethyl cyclohexane. So instead of having them on neighboring carbons, they're one away from each other. So let's look at those really quickly. 1,3-disubstituted cyclohexane rings. So again, we have cis and trans. This time though, because they're on numbers 1 and 3, let's draw this here. If this is axial, 1, 2, this is axial. I should have used a different color. Let's see, let's do yellow. The axial is here and here. And then equatorial will be here and here. Oh, I used the same color. Need to do something there. Let's just use white. Equatorial's here and here. So notice again if it's, so this is a top and this is a bottom. This is a bottom and this is a top. Because they're one away from each other, they're the same, they have the same shape. And so for cis, they're both going to be on the either both tops or both bottoms. So let's draw. Oh, we could use that. So they're either both going to be axial. That would be very high energy, right? Because they're even going to have interactions between themselves. And then let's draw down here, or they're both going to be equatorial. And so there's going to be no interaction between them at all. So again, this is the top and this is the bottom. So we've got, and that's the bottom and that's the top. So if this happens to be it, we're going to have, they're either both going to be axial or they're both going to be equatorial. That's the cis form. What about the trans? The trans form means we have to have one axial and one equatorial. So let's erase these here. So again, this is the top and this is the bottom. So for trans, we're going to have to have one on the bottom and one on the top, which means we're going to have one axial and one equatorial. And then if they do a ring flip, they're going to be one equatorial and one axial. So again, just like the 1, 2 cis, the 1, 3 trans will have one axial, one equatorial, so they'll be pretty equal in energy. The 1, 3 cis will be a lot like the 1, 2 trans, where it'll be locked because one will be much higher energy than the other. I think that's on the next slide. So again, here's cis. Let me get my pointer. Here's cis, where they're both equatorial. If you do a ring flip, they're both axial. Very high energy because not only do we have a CH-H interaction, we also have a CH3. If you remember from the last chapter, they were actually like 11. So this is very high energy. But the trans 1, 3, because they're on opposite, one on the top, one on the bottom, when they ring flip, we're going to have one on the, so this is axial equatorial. Even though this is top and this is bottom, this is still top and this is still bottom, but now this one's axial and that's equatorial. So they're equal energy no matter which way they flip. So it depends on if they're 1, 2 substituted or if they're 1, 3 substituted, and then it also depends on if they're cis or trans. So you're going to have to look at each situation individually. Now the last possibility is 1, 4 substituted, 1, 4 disubstituted, and that goes back. It looks like the 1, 2 because you've got because they're on two different types of carbon, one where the axial is going up and one where the axial is going down. So so they're going to look just like the 1,2 disubstituted. So this is just a nice refresher. The 1,2 cis is either going to have axial equatorial, or when it ring flips, equatorial axial. So equal energy. I'm not going to be able to write that very well, but so I'll just put an equal sign, equal. Let's do blue. Here, 1,2 trans disubstituted, they're either both going to be axial or they're going to be both going to be equatorial. So equatorial will be lower. So there's going to be a higher percentage of this form. Now, flipping it, 1,3 cis disubstituted is just like 1,2 trans. So again, the 2 equatorial is going to be lower. But the 1,3 trans is going to be equal, pretty much. Now the 1,4 cis is just like the 1,2 cis, where they're going to be equal. And then I'll just draw that down there. The 1,4 trans, they're going to be either both axial or both equatorial. Now these are going to be, because we're talking about the same, so far we've only really been talking about methyl groups each time. So they're equivalent. So what happens if the substituents are different? Oops. What happens if the substituents are different? Then you have to analyze a little bit even more. So let's look at this one, cis 1-ethyl 2-methyl. So now the ring flip, and it's cis, so we've got a top and a top, so they're both tops. It just happens that this top is equatorial and this top is axial. If you do a ring flip, then this one is equatorial and this one is axial. Well, when they're 2 methyls, then they're equal because it doesn't matter which one's axial. But if they're 2 different groups, what you'll have to take care is that the one with the less energy should be axial. So in fact, this one's a little more unstable because the big group is axial, where here the smaller group is axial. So sometimes if you're not sure which group is higher energy, you can go back and look at that chart, which was a few slides back. So like, let's say this was the CN and the CH3, then the CN would prefer being axial. So the one with the lower energy prefers to be axial if you have to have one of each and they're different from each other. All right, so here's just an example. Let's look at it. Which is the more stable conformation for cis 1-chloro 4-T-butyl cyclohexane? So we have our 2 possibilities, and it's cis, so they and 1,4. So here's the 1 and here's the 4. Since they're cis, they both have to be tops. And let me draw the other hydrogen in so you can see the chlorine is a top and the T-butyl is also a top. That both of this is a bottom and this is a bottom. So to be both tops on 1,4, they're one's axial and one's equatorial. So what kind of interactions do you have here? We have ClH, ClH. Well, Cl is 1 and there's 2 of them. And so this is 2 kilojoules per mole steric strain. If we do a ring flip, what happens is now the Cl, let's go back. The Cl is on top, it's equatorial. The T-butyl is also on top, but it's axial. So this is my bottom and this is my bottom. Just you can see, just because they're different types of hydrogens, just because one's the top and one's the bottom doesn't have anything to do with axial or equatorial. So now remember the T-butyl group had 11.4 kilojoules of energy. And so this would be 22.8 kilojoules. So even though there's no gauge interactions because they're far apart, clearly this is much more stable. There's still a little bit of energy there, but it's much more stable. So it's pretty much the big group's going to be in the equatorial position if they have if you have to pick one or the other. All right, let's do one more example, and you might want to try this before I go on, and stop the video and do it before you go on. Draw the two possible chair conformations of menthol and indicate which is more stable. So notice that this is sort of a flat cyclohexane, which is not true to what it should be. But you can see that this is up. The OH and the CH3 here are cis to each other, and this this would be an isopropyl group, is trans to both of those. All right, so let's look at it. So when you draw this, it doesn't matter where you put the first group, but once you put the first group, you want to make sure that all the others are in the right position. So let's say I'm going to start with the CH3 and I draw it on top. So it's the top. It happens to be equatorial, but it's out of the top of these two. And then the OH is 2 carbons away. So here's carbon number 1, well, the CH3. 2 away is this one. I also want the OH to be on top, right? So it also, in this case, happens to be equatorial because they're 2 away from each other. Then 1 more carbon away, which is this carbon here, is the isopropyl group. And because it's going to be the bottom, it's going to be this one right here. It happens to be the equatorial in this case because it's the bottom of the 2 carbons. All right, so like I said, you want to make sure that you can start anywhere. If I started with the CH3 here, then I would have the OH here on this carbon, and I'd have the isopropyl group here. So it doesn't matter, but you just want to get them the correct number of carbons apart, and you want to make sure that they're either cis or trans to each other, cis and then trans. So here's one, and then all you have to do is do the ring flip. So this CH3 goes up, and it's right here. This OH goes up, becomes axial, and then this isopropyl group actually goes down, and it's also axial right here. So notice in this case, menthol has either all 3 axial or all 3 equatorial. So what do you think is the more stable? Of course, all of them in the equatorial phase. So I think you would find nearly 100% of menthol in this conformation. All right, so we just have a few more slides. I know this video is going a little bit long, but let's just finish this out. So Decalan, and I'm not going to focus as much on these, but I just want to introduce them to you. So Decalan actually has 2 cyclohexane rings joined together, and they share 2 carbons at what's called the bridgehead. We'll show a picture on the next slide. There's 2 isomeric forms of Decalan. One is trans and one is cis. I think you could come back and read this slide afterwards. I have to keep going forward, but come back and look at this. So the cis Decalan, the hydrogens on the bridgehead are on the same face of the rings, and then in trans Decalan, the bridgehead hydrogens are opposite. So just what you would think, cis on the same side, trans on opposite sizes. They can both have their 2 chair cyclohexanes stuck together, and then when they flip, they don't interconvert, cis and trans. So anyway, let's just take a picture, take a look. All right, so here's sort of the flat look, but remember, this is a 3-dimensional molecule. Decalan has 10 carbons, but it's not decane, it's not cyclodecane, because these carbons are actually connected as well. So it's 2 6-membered rings stuck together. So here's the cis Decalan, where you can see that the 2 attached carbons are both bottoms in this case. So the 1H is axial, that's a top, and this is a bottom. This is I can draw that in for you. So this is a top, and this carbon's the bottom. Here, this is the top, and this is the bottom. So you can see that the two carbons, this one is a bottom and this one is a bottom. So that's why it's cis. But that's a very funny looking molecule. So here's this one chair, and by necessity, because this is a bottom and this is a bottom, this ring kind of, you can see the picture over here. This kind of goes downward. So that's cis-decalin. And then here's trans-decalin, and notice that this time trans means one has to be the top, which is this. This is the bottom. Here's the top again, and then here's the bottom. So in this case, we've got trans, so one of them is a equatorial top and one's an equatorial bottom. They're both equatorial, and so that makes these two rings sort of low and flat. So you can imagine there's a lot of different physical properties between them. They're very different, even though they have the same formula. Which do you think is more stable? Well, I would say having both of these, all of these equatorial, all these carbons equatorial has got to be more stable, whereas this one has one axial. So the trans will be more stable. This is just showing you extending it out. So if you get a picture of here's a steroid, testosterone, and when you draw it flat, you don't really get a good idea of what the molecule looks like. And you see, well, this has the double bond, but anyway, it's actually got that decalin right here, and then it's got a 5-membered ring attached. But notice that those two, this is the trans decalin, where the two carbons are attached right there, and they're both carbons are equatorial. And so anyway, that's probably going to be the more stable, and you're going to see it in your all kinds of molecules that exist in life will have the more stable one generally. And so testosterone, a lot of steroids have this shape. One other thing just to introduce to you, and is not really important, is this norbornane. I can't even pronounce it. Well, the main thing is that it's a bicyclo. So you notice that there's two, here's a cyclohexane, and then there's another ring attached. And so it's kind of a funny shape. This is the official name. It's a bicyclo, meaning that there's two rings fused together. And what these numbers mean is that there's this bridge, this is called the bridge head, where the two rings are fused together. This is one bridge here that has two carbons. Here's another bridge that has two carbons, so that's where the 2 and then the third bridge only has one carbon, and then the heptane means that there's 7 altogether. So let's say, let me see if I can get my picture here. Let's say instead we have a 222 octane. It would look sort of like this. Not a very good drawer. But again, here would be our bridge heads. And then we'd have 1, 2, 1, 2, and then this one, you can't see it very well, but there's one here and then one here. So this would be bicyclo 222 octane. So I'm not really going to get into this on tests or anything like that, but you may see it again, and so I wanted to make sure that you knew what that was. And this is just, I just wanted to point your attention to, if you're the end of the chapter, it talks about molecular mechanics, and it talks about how all these structures that you see in your textbook, how do they come up with these pictures? How do they take something that's two-dimensional and create it and know that that's the correct structure? Well, it takes a rough geometry, calculates the energies using all those different steric, torsional, angular strains, and then configures it to show what it would look like at the lowest energy possible. And so that's that's how they get these pictures. This is Tamiflu, so that's very interesting. So, of course, the two-dimensional shape doesn't tell you a whole lot. And that's the end of this.